Welcome back, everybody, and to this session, which is going to be a session where we are going to look at some specific applications of Hartree-Fock theory and how we can actually interpret data. And one of these, it's not exactly a theorem, but it's normally called Koopman's theorem. It's actually an approximation, but it gives us a kind of intuitive feeling of what the Hartree-Fock energies actually mean. And then we are going to look at the stability of the Hartree-Fock equations, which also gives us some insights about the matrix elements which are involved, and whether we can say something about the strength of the interaction and the single particle energies, and whether we are going to get a converged result or not. Because the Hartree-Fock equations are solved as an iterative set of equations. They are nonlinear in the unknown coefficients. And then we solve these equations iteratively with a guess. Now, you may remember from some of the linear algebra iterative methods, like there is a method which is called Gauss-Seidel, or just Jacobi's method, which are iterative methods. Now, these methods converge to the exact solution. This is a typical linear algebra problem where you have a matrix A times an unknown vector X, which is equal to a right-hand side B, which is known. You can start with a random guess, and that will always converge to the exact solution if the matrix A is semi-positive definite, which means that that matrix has eigenvalues which are larger or equal than 0. Now, the Hartree-Fock equations, what we will see with the stability studies is that this applies to the Hartree-Fock equations as well. So we normally start with a guess for the unknown coefficients, and the way we wrote the equations last week is in terms of an expansion in using an orthonormal basis, and then we make an expansion where the expansion coefficients are the elements of a unitary matrix. So we have a unitary transformation of the basis, and then we get a new basis. And these coefficients are the coefficients which we find by solving the eigenvalue problem with Hartree-Fock. Now, in the midterm, we are going to do that with the Lipkin model. And for the Lipkin model, you have analytical expressions for these coefficients. And in this specific midterm, we don't need to write any codes for solving the Hartree-Fock equations because we have analytical results. But feel free to do that as well if you want to, an extra challenge. The midterm, which we will also discuss in more detail tomorrow, is based on some of the weekly exercises, and you will see that 1 and 2 of the exercises are pretty close to what you did during the weekly exercises. So this is just to get you started again. And then the beginning of the exercise assumes that you have seen the solution in the weekly exercises. I'm going to send that solution to you for the rewrite of the Hamiltonian in terms of quasi-spin operators. Then on Friday, we will also look at the, if we don't finish this part today, we will most likely continue with it on Friday. And then we are going to start with a famous system. We also have analytical solutions for the Hartree-Fock equations. So this is an infinite system, but normally you discretize it and you run the calculations in a periodic box with periodic boundary conditions. And then you have a given number of particles and a length of the box, and that translates into a density. Now, the electron gas, the homogeneous electron gas in 3 dimensions, has been used as an extremely popular model in solid state physics, in condensed matter physics, especially in order to understand the properties of semiconductors. So you would have a layer with ions, which make a background uniform charge, and then you would have electrons which are affected by this layer of uniform ions. We are coming back to that. Now, the electron gas, for those of you who study density functional theory, is also interesting because it provides an approximation to the exchange term in density functional theory. And this is normally called the local density approximation. So the homogeneous electron gas is an interesting system by itself. We can solve it analytically. which is also very interesting. And at the same time, it provides the input to a many-body method, which is called density functional theory. And we are going to scratch a little bit the surface of density functional theory before we then, for the rest of the semester, we are going to move over to perturbation theory, and we can decide whether we want to do Green's function theory or copper cluster theory, which is another many-body method. And that's going to be the end of the semester, basically. Okay, so I wanted just to say something, and I will be using the slides for the analysis of what's called Koopman's theorem, and then we go back to the whiteboard. So the thing which we did last time was actually to rewrite the Hartree-Fock equations in terms of, obviously we have this expectation value. So we defined something which we call the U Hartree-Fock potential. And the Hartree-Fock potential is actually given by this sum over the states below the Fermi level. And this U Hartree-Fock gives us then a potential which has the one-body part from the two-body interaction. And we could rewrite that in terms of this equation which you see here, where these epsilon i's are the Hartree-Fock energies. Now, in atomic physics, this is very much used in order to look at ionization energies. So what you're making as an assumption, and so if you look at the Hartree-Fock equation, now I'm just writing it out in terms of the Hartree-Fock basis here. So these are essentially the Hartree-Fock equations which we have. Now what you can do then is that you can take away an electron from the system. So if you're thinking of sodium, which has 11 electrons, and the last electron is in the free s orbitals, if you make such an atomic physics model. And then if you take out one of these electrons, that means that the energy of this system is the Hartree-Fock Slater determinant for n-1. Now comes an assumption, and this is why sometimes you wonder why this is called a theorem, because the assumption is that these single particle states don't change when you move from one atom to another one where you have removed an electron. So if you take sodium, so let me just put that on the drawing board there, so you see the usefulness of Koopman's theorem. So let me just bring that up, and let's look at a simple example. So in Koopman's theorem, and we are going to look at an example which could be neutral sodium. So we have Na, and that has 11 electrons and 11 protons, which make up the charge of the atomic nucleus. And then there are 11 neutrons in the standard sodium nucleus. But you can have different number of neutrons if you want to. Then you have isotopes of sodium. In this specific case, what you have is you would have the inner shells, 1s. If we are now thinking in terms of atomic physics, we have a 2s, and normally these are, the degeneracy is lifted. So you would have 6 electrons in these orbits. And then you have 2 in the 1s, the inner orbit, and then you have 2 in the 2s orbit. That would make up a model for the noble gas neon. But then you have an additional electron, which is assumed in this single particle picture to be in the 3s. Sorry, not that one. This is a 3s state. Now, keep in mind, and this is actually very important, and you will often hear experimentalists and other, even theorists, claiming that they are looking after the single particle properties of an atom or a nucleus or solid. Single particle properties are not observable, period. So what is an observable is the energy of a many particle system. Sadly, there are actually many people who think you can, and they even make research proposals where you can extract single particle properties from experiment. So what you observe essentially is the energy of a system. and this is a many-body system. But you can make interpretations of it. And this is what we are doing. So this kind of single particle basis we are using, there's nothing magic behind it, but we see properties which can be interpreted in terms of a single particle basis. It does not mean that you can measure the energy of this free S state here. Now, what you can have is the ionization of sodium, and that means that you would get a sodium ion where you've taken away the outer electron, which is the weakest bound one. And you can then interpret that in terms of a free S electron. It doesn't need to be that one. However, if you use atomic physics, and the success of the model for atoms and also molecules is actually based on this interpretation. The whole shell model or the shell structure of atoms actually follows this kind of physical interpretation. So it's a meaningful interpretation. It doesn't need to correspond to reality, but it's actually an interpretation of reality, which is meaningful. And it's also based on many of these observations that the Pauli principle was postulated. Now, the Pauli principle simply states that the total wave function of such a system has to be antisymmetric. When you then translate that into a single particle basis description, then you cannot have more than one electron in one of the single particle states. So it's important to keep, I'm bringing this up again because it's important to keep this in mind, because it's easy to be led away with Hartree-Fock theory because it gives you a simple physical interpretation of what is going on. So Hartree-Fock theory, when we take the difference, so one of the reasons why Koopman theorems works fine, even if we're assuming now that the single particle states for electrons in neutral sodium and ionized sodiums are the same, there's a reason for that. And the reason for that is that the number of protons stays the same. So the number of protons set up an attractive field which traps the electrons. Now, the number of protons doesn't change. So the major contribution to the binding energy or to the energy of the system comes from the atomic nucleus and the attraction from that. Now you also have to be careful because we are looking at electronic energies only, and they come out in electron volts. The energies which come from the atomic nucleus, which you would have in here, which has obviously a reach of something like 10 to the minus 15 meters. The atomic sodium has a radius with the electrons of something like nanometers. So we are talking about 6 orders of magnitude from 10 to the minus 15 to 10 to the minus 9. And we are only looking at the electronic degrees of freedom, which means that here we are looking at the scale of electron volts, and we are neglecting the atomic nucleus, which has a scale, energy scale of giga electron volts, which is 9 orders of magnitude compared to the electron volts. So we're actually looking with a magnifying glass here and at the specific energies of the electronic degrees of freedom. Within that effective space, or these effective degrees of freedom, it makes sense to approximate this system here as a system where the wave function of an electron in ionized sodium is basically the same as the one in neutral sodium. That's an approximation which is made. And that's the assumption behind Koopman's theorem. If you do that, then we can calculate the energy when we take out one electron. And that energy difference is going to be the Hartree-Fock energy. So that's why Hartree-Fock is such a useful theory, because it gives you a guidance and a kind of, how to say, useful interpretation of what it means. But that relies on the fact that you assume this single particle picture. And when you make a measurement, you can never measure a single particle property. You're actually measuring the energy of ionized sodium with respect to neutral sodium. But when you run a Hartree-Fock calculation, that energy which you get is pretty close to what you observe experimentally as the energy difference between ionized sodium with 1 electron stripped and neutral sodium. So that's quite interesting. And that's why this single particle picture is so strong as a tool to interpret many body systems. But we always have to keep in mind, since all of you are theorists, that there is no such thing as a single particle observable in a many body system. You are observing many body quantities. So during a break, I can tell you of all the research applications where people actually wanted to observe single particle properties. And these research applications obviously were returned with a refusal on fundings. Okay. So let's go back to the slides here, because I just wanted to go through the slides. So what we have then is that we can simply set this up. We take away electron in a state K. So we simply make the summation without electron K in both sums. One is a single sum and one is a double sum. And then if we take the difference, so you could think of this as neutral sodium, and you run a Hartree-Fock calculation for that, and you simply calculate the same as with the same single particle basis, and you calculate the energy of ionized sodium where you've taken out 1 electron. Suppose you can run these calculations, or you can make an observation. So you could measure these quantities experimentally. You can actually measure the ground state energy of neutral sodium and ionized sodium. Then you can show that this is the same as these two terms, and this term which you see here, when you add these two, because you have a double sum, so you have to look at one case where I is different from K, and the other one where J is different from K, and you can rewrite that as two sums, which means that this is nothing but the Hartree-Fock energy, which we defined earlier. So if you run a Hartree-Fock calculation and you get the single particle energies, you can actually obtain this as a first ansatz for the difference between a many body energy and a many body energy minus 1 particle. But the assumption is that these single particle states do not change. So it's useful in atomic physics, because in atomic physics, a large contribution to this single particle energies comes from the protons which you have in the atomic nucleus. So the larger that charge, the more important the contribution from the nucleus becomes. Does that sound reasonable? So in atomic physics, the interaction is in general weak. And then a lot of the binding energy of a given electron comes from the attraction from the atomic nucleus. So you can then make an interpretation, and you could replace these with experimental values and then see how well that compares with a Hartree-Fock calculation. And in atomic physics, these numbers are not so different. And this is something which has actually led to this interpretation of single particle degrees of freedom as a kind of effective degree of freedom. But just keep in mind that experimentally, when you observe energies, these are the energies of many particle systems. And you can do the same. So this would typically be the ionization energy. And this, if you add 1 particle, you would then have the above the Fermi level Hartree-Fock energy. And this is normally called the affinity energy or addition energy. And you can repeat the same in fields like nuclear physics. And in nuclear physics, what you would have then is something which you can extract from experiment, which will be the binding energies. So you can actually find the binding energies of a given atomic nucleus with protons and neutrons. And you can take these energy differences and you would obtain the same results with Hartree-Fock theory. And then you could interpret these energy difference in terms of these single particle energies. Now, in nuclear physics, the interaction is much more complicated, and it is not as weak as the Coulomb interaction in atoms and molecules. which means that this is not a very good approximation in many, many cases. So this is Koopman's theorem, and it just is based on you having assumed that the single particle states do not change when you take away one electron. And in atomic physics, it's a decent approximation because the atomic nucleus is the one which provides a large fraction of the binding energy and the structure of the single particle states. But calling it a theorem is a little bit, how to say, strong, but it's just established in the literature as Koopman's theorem. So what I want to do now is actually to go back to the slides, and I want to discuss a little bit about the stability of the Hartree-Fock equations. And we are going to make an analysis now of the equations, and you will find this much of the same information in the slides, but let's slow down the pace a little bit and move over to the whiteboard. So we are going to look now at the stability of the Hartree-Fock equations. And we can actually, by rewriting them in second quantization, we can say something about whether the equations will converge or not, depending on the size of the matrix elements and the single particle energies. And you will find that useful in the midterm, because the last exercise in the midterm deals actually with the stability of the Hartree-Fock solution as a function of the strength of the interaction. So what you're going to see now is something which you can translate into the midterm, except for the midterm, the Hamiltonian is much simpler. And we just have a constant for the interactions. So we never deal with an integral which is dependent on the single particle wave functions. So let's take a look at the Hartree-Fock equations and the stability. So there's one theorem which we are going to show a little bit later, and that is Fowler's theorem, but we are going to use Fowler's theorem first. So what we have done is simply to assume that there is a Hartree-Fock state, and I'm going to rewrite this in a little bit compact way. I'm just going to write this as C, which stands for core. So that's the core energy. This is just the reason why I write C here. It's just plain laziness. I don't want to write phi, 0, and Hartree-Fock and all these things. So just C now is the Hartree-Fock state, which we have obtained with the Hartree-Fock optimization. And this is something which now is given in terms of these creation and annihilation operators. So we would have an A of I dagger acting on a true vacuum. So this is in second quantization now. Now, what Fowler's theorem says and we will prove it later. What that says, and that's extremely useful theorem, especially when we later are going to link with couple cluster theory and the exponential ansatz for the wave function. So Fowler's theorem states that we can write a Slater determinant C prime, which is given as an exponential, and then it's just a sum over particle hole excitations. So this is a linear combination of particle hole excitations to infinite order acting on the state C. And there is a basic assumption here now. So what it says now is that we have a general Slater determinant, which can be written in terms of these other Slater determinants as a linear combination of particle hole excitations. So the assumption here is that there is a non-zero overlap between these two Slater determinants. So I can write a Slater determinant, a single particle based many-body wave function in terms of a linear combination of particle hole excitations. So this is what the theorem says. We're going to prove it a little bit later, but now we're going to use it. So what we did actually earlier is that we made a Taylor expansion of this quantity. So what we can do now, if we Taylor expand, we can now say that we have a prime quantity, which is now going to be equal to the first one, which we had, plus, and then I have an AI, and then I have my CAI of AI dagger AI, and this is acting on the vacuum state, plus, and then I have 1/2, I have a double sum AI, and then I'm going to rewrite this one in terms of a BJ, so it's going to be a CAI, CJB, and then I have AI, AI, and then I have my AB, AJ, and this goes on since we are Taylor expanding, and we can put parentheses here like this, and this acts on C here. So what we are going to do now is to truncate this approximation at first order. So we're going to assume now that there are some small changes in these C's, just minor changes. So I'm going to replace this term here with a delta CIA, and I'm going to assume that this is small. So we are going to truncate this summation at first order. This is a pretty common approximation. So we are going to replace the CIA with a small change. So we make a small perturbation. And that means that we are going to approximate this Slater determinant now with just a C, the original state, plus a sum over AI. And now I have a delta CIA. And then I have AI, AA, AI acting on C. And this is going to be my change, which we discussed earlier when we did Hartree-Fock theory. So we have the original state plus some change. And that change, which you see here, is a particle Hall state. And that is obviously orthogonal to the state which we started with. Okay? So this represents a one particle, one Hall state, where we make a simple small variation in this coefficient. And we are assuming now that these coefficients are small. So what I want to do now is simply to calculate the expectation value. So if we assume now that the C of the Hamiltonian of C is given by the E0 Hartree-Fock. So if this is the best minimum we can get, so if E0HF is the best minimum we can get with Hartree-Fock theory, so let's put this in quotation mark. Since I can write a new Slater determinant in terms of that expectation, that state C plus a small variation, that means that what I need to test now is actually to calculate this expectation value divided by the norm. In the previous case, I have assumed that my state C is now normalized, is an orthonormal, constructed from orthonormal states, so we don't need the denominator. So what we would have to demonstrate now is that this one is larger or equal than E0 Hartree-Fock. So the idea is that we have a general Slater determinant, which now contains the previous one, which gives the Hartree-Fock energies, plus a small variation. So if Thule's theorem, if we agree that that holds as a theorem, it means that there are tons of Slater determinants, which are linear combinations of one particle, one Hall excitation. So what we need to show then is that the state we found by the Hartree-Fock calculation is a minimum. So that gives a lower energy than all the other possible Slater determinants which I can make. Keep in mind that we are still using a Slater determinant as a basis, which means that when we calculate H with phi 0 Hartree-Fock, this is not an eigenstate of H. Okay? So this is not the same as the true ground state times this one. So the Hartree-Fock state is an approximation. And it's simply, as you have seen in the exercises, it's simply a Slater determinant. And that means that it contains essentially, as we also have discussed with Hartree-Fock theory, at most one particle, one hole correlations baked into the states which we have. So keep in mind that we discussed last week that Hartree-Fock theory can be seen as a unitary transformation where you zero out the coupling between the zero particle, zero hole state with one particle, one hole states. So that means that what we have is a similarity transformation where we have zero out specific elements. And these specific elements come from the contribution of one particle, one hole states. So, but we are still staying at a wave function which is based on a product of single particle wave functions. And that's the Slater determinant. Okay? So this is the basic assumption we are making, which means that what we get as a Hartree-Fock state is not the true ground state, but hopefully it is getting close to the true ground state. So what we want to find now is whether this state here is the best optimal minimum which we can get. And then we need to prove that the other expectation value is larger or equal to the Hartree-Fock one. Does that sound reasonable? The basic assumptions we are setting up? So what we are going to do now is simply an exercise in contractions and Wick's theorem. And we are going to calculate the different contributions. And since we now have stopped here, so we stop at first order in delta C, that means that when we now calculate the expectation value of this energy, which we have here, and this one, we are going to stop at contributions which go like delta C squared. Because when I calculate a norm here, that will contain obviously C with itself. It will contain C with this guy here, which will be 0. But there will be a term which goes like delta C squared. And we are going to stop the energy calculation at that level. So we truncate the wave function at first order here, but that means that the energy and expectation values will have to be truncated at delta C squared. Okay, so let's continue now and set up the basic calculations, the basic elements which we need. So one of the things which we can see immediately when we now calculate this quantity C of C here, so let's just look at the calculations. So that will obviously contain C of H of C, and we know that one, that is the Hartree-Fock energy. We don't need to calculate that now because we have calculated it. So this is E0 Hartree-Fock. Then we're going to get a term which goes like delta C of H of C plus a C of H of delta C, like that. And these have some nice values. So what should they be like? So say again. 0? Yeah, because this is a 0 particle, 0 hole state, and you have H, and you connect that with a 1 particle, 1 hole excitation by constructions. Because if you look at your 1 particle, 1 hole state, that is the one which you have here. So this is a 1 particle, 1 hole state. And since we have a Hartree-Fock basis, when we've run the, so we have run the Hartree-Fock calculation, we know that this one is set to 0. So that was the constraint which we put on the Hartree-Fock calculations. So that means that these two terms are actually 0. And then we need to evaluate the higher order terms. And the higher order terms are going to give us 3 more terms. And we now need to be a little bit careful when we write them out. So let's write out these terms, the higher order ones. So we are going to have plus, I'm going to have a term which goes like AI dj. There will be a delta CIA. So because we will have terms now, or let me just write them, keep this general way of writing them, because then you see it a little bit easier. So we will get plus a delta C of H with delta C. And then we are going to get a C with H of delta C squared plus the Hermitian conjugate, which is a delta C squared of H with C. And we are truncating at second order because we truncated the wave function at first order. Okay? So let's now try to calculate these terms. And let me also remind you of the fact that these two guys here are actually equal to 0. So let's remind you of that. And then we calculate this one. And we're going to calculate this one and that one. And this is going to be an exercise in just using Wick's theorem. Then when we set up the contractions, we can then rephrase everything in terms of a matrix eigenvalue problem. And then we can look at that matrix, and from that matrix, we can require that the eigenvalues of that matrix have to be larger or equal than 0 in order for that E0 Hartree-Fock to be the optimal minimum, which we get from the Hartree-Fock calculation. So let's remind ourselves about some of these calculations here. So if I take this term, delta C of H of C, this is the same as when we write everything out. We have a sum of a particle Hall states. Now we have this tiny change. So this is a complex conjugate. And then I have my state C. And then I have my AI of A, and H, and C. So if we now remember how the Hamiltonian looked like, what we are going to get now are two different contributions. So one is C of AI of AA, and then we have the one body operator, AP and AQ of C. And here the only contractions which I can have are these contractions here and this contraction here. That's the only one I can have. And what we did then with the Hartree-Fock equations, we actually required that this term had to be equal to 0. And that gave us, when we set up this term here, it gave us a specific matrix element which went like A of F of I. That's what this gives us. And then we had the second term of C of AI of AA. And then we had the two-body operator. So this is from the Hamiltonian here. And then we have S and R and C. And in this specific case, we can perform one of these contractions again. And this could contract with that one. But then we have always parts of an operator contraction with the operator itself, which then automatically leads to 0 when we use Wick's generalized theorem. So this term, which you see here, is automatically 0. And all its possible contractions, plus other contractions. Now, when we set up the Hartree-Fock equations, what we did then was to require that this term here, that this term is actually equal to 0. And that led to the equations which are used to determine the Hartree-Fock recipe. So we require that that one is equal to 0. And one way to solve that is, which fulfills it, is that the basis you have is an eigenbasis of this operator F. So let me remind you also of the operator F. So this F, or this A of F of I, is the same as the single particle piece of A of H0 of I plus the sum over all states below the Fermi level and then we have I and AJ of V of IJ anti-symmetrized. And one way to fulfill these equations was then to define the Hartree-Fock single particle operator. And then we require that H Hartree-Fock of I is equal to epsilon I Hartree-Fock of I. So this is now the eigenbasis of a new operator. Previously, we started with a set of states which were the eigenstates of this one. But when we run a Hartree-Fock calculation, the new single particle states are the eigenstates of this operator here. And additionally, we required that HF of A is equal to epsilon A Hartree-Fock of A. And this is one way to implement that condition which we have. So Hartree-Fock theory led to this condition, and this is the same as 0, which we then could simply say that when you look at this eigenvalue problem, this is the same as epsilon I multiplied with a Kronecker delta of AI, and that Kronecker delta gives 0. So that was one way by which we could implement this specific condition which you see here. So this is the result of the Hartree-Fock recipe, and that requires that that matrix element has to be 0. One way to obtain that is simply to require that you have the solution to these two equations here, so that these I's and A's are the eigenbases of that operator. And then you see immediately if this is an orthogonal basis, then this condition is fulfilled immediately, because then A and I cannot be the same. Okay? So that first element follows from the Hartree-Fock criterion. So what we're going to look at now is the next element. So let's look at the element which is given by this delta C of H of delta C. So this is an element which is not necessarily 0. And if we write it out, it's going to be a sum over AI. It will be a sum over BJ. I will have a delta C IA, and then delta C JB. And then I'm going to have the matrix elements where I have a AI dagger, AA, and then I have the operator, the Hamiltonian, and then I have my A, B dagger, AJ, and acting on C. So what I need to do now is simply to look at the possible contractions which I can get. Okay, so let's do that. So the first one which we get now, when we look at it, is a contraction between C, and then I have my AI, AA. So this is the brass side of the one particle, one hole excitation. And then I take the one body operator, AQ, and then I have my AB, AJ of C. So one possible contraction here is simply that this contracts with that, and then this with this one, and that with that one. So that gives me delta IJ, so the whole states are unaffected by the one body operator. And then I have a delta AB, and then the one body operator now runs like A of F of B. And that is simply delta IJ, delta AB multiplied with a Hartree-Fock energy A, like that. And let's just do one more before we take a small break. So the next one, if I look at these guys here, I have an AI, AA, AP, AQ, AB dagger, AJ, and C. Now I can contract the whole states. So what I could do now is simply to take the AI going to AQ here, sorry, like this, And then I can take AP going to AJ. So this gives rise to a minus sign because I have to interchange operators. And then I would have my AA with AB. So when I set up the interchanges, I get a minus sign. I have a delta AB, and this is going to be given by epsilon I Hartree-Fock. So these were the two first contributions with a one-body operator. And then after the break, we are going to do the two-body operator. And then we will get some explicit matrix elements which come in addition here. Okay. Any questions so far? Things which are unclear?
I have one question about the previous slide.
Yeah.
So you're saying that this matrix element A and I is the one body operator.
Yeah.
And then some two body.
Yeah.
And I just assuming this sums up to zero, the sum of the two.
Yeah. So this this one, right?
Okay.
So when we derive the variational calculus-based approach, then in order for the equations to be fulfilled, we had to require that. We actually required that this has to be zero.
Yeah.
And
so like this is zero if you go back to the slide.
Yeah, so this is zero, because when you do the contractions, the only one which you get is actually that one.
Yeah, so you go to the next slide again. No.
That one, yeah.
No, you write it out as one body and two body, and then you show that the two body is an eigenstate.
Yeah.
Like zero, since all of them are different.
Yeah.
But what about the fact that some of them change?
So this is the new basis you're constructing. So the whole operator contains now the one body part which I had before, and then this piece which comes from the two body part, because this acts like a one body operator. So we have a modified one body operator, and that one modified one body operator comes from you rewriting the Hamiltonian in normal ordered form with respect to a new vacuum. So you get a one body part and a two body part.
Yeah. And the two body part is zero.
The two body part is automatically zero because you're connecting, and you can see that because you're connecting a one particle, one hole excitation with a zero particle, zero hole.
Yeah.
So it's only a one body operator which can bring you from one to the other one. A two body operator would require that you end up in a two particle, two hole state. So that's automatically zero. So you can actually look at this expectation value and think in terms of excitations. And then you can immediately say, okay, I have a two body operator at most. It contains one body parts. The one body part can make a one particle, one hole excitation, but the two body part would immediately make a two particle, two hole excitation. And that doesn't match. And then the variational principle leads to this guy here having to be zero. And this is something we showed last week or the week before. And one way to fulfill that, one possible way, is to require that this eigenvalue equation is satisfied. Because then the basis is immediately orthogonal. And then these two guys have to give zero, this piece here. So I'm going to put the recording on pause and get started. Okay, so the what we did before the break was to look at the contributions from two possible terms with a one-body operator. So the thing we need to look at now is the contribution from the two-body operator. So what we're going to do then is the final term where we need to set up these other contractions. So let's just write this as a number 3 here. So now we need to look at these contractions here. So we have an AI, and then we have the two-body operator. And then we have this AB and AJ acting on this Hartree-Fock reference state. Now, in this specific case, now we can look at contractions between Q and S. So this would be a particle state. And we can do the same with P and R, if we want to, like this. Then what we would have next would be a, oh no, sorry, this was not correct. I just fooled myself a little bit here. Let me just read AP dagger. And then we have AQ and AS. So we can have a contraction here with A and P. So this will be a particle state. We can do R and B. That is also possible, so that R becomes a particle state. And then I can now do A with S. That's also non-zero contraction, but this is a whole state. And then I'm going to have to interchange operators, which is something you can quickly see if you have crossing lines when you link together the different contractions. So this is going to give rise to minus delta AP, delta of the SI, and then I have a delta of QJ, and then I finally have my delta R and B, and this is multiplied with a matrix element PQVRS, anti-symmetrized, and it's also multiplied with a factor of 1 divided by 4. So if I plug in things, I would get minus 1 divided by 4, and then I'm setting up the matrix element, and then I can rewrite this one in terms of an A here, and then I have a J. This is anti-symmetrized matrix elements, and then I would have a R, which is equal to B here, and then S, which is equal to I. So I could have a B and I here, anti-symmetrized. Now I can, if I don't want to have the minus sign, I can change this by just interchanging two of the states. So I could get a plus of 1/4, and then I can have a AJ V of IB here, anti-symmetrized. And if I want to write the Feynman diagram for this specific part, the diagram here would look something like this. So I have an outgoing particle state, A. I have an incoming particle state, B here. And then I have a whole state, J, which comes in here. So this is the whole state J to the right. And then I have a particle state I here. So this is something which I would call a one particle, one hole excitation, because I start with a one particle, one hole state here, and I end with a one particle, one hole state here. And when you look at the matrix elements which we were setting up, if you go back here, what we have is a one particle, one hole state here, and a one particle, one hole state here. So when we perform the contractions, we can actually look at the diagram and simply state that this is a diagram which corresponds to one particle, one hole excitation. But then this is a direct term. So this would correspond to the piece which is given by A of J, of V, of I and B. But then, so this is this piece. But then we have an exchange term, which would be A of J, of V, of B and I. So what we would have then would be a diagram which would look like as follows. So this comes with a minus sign when we read it. So we have the interaction line. So we have an A going out, a B coming in to the left. So that's on the left on the state here. And then we have a whole state I and a whole state J here. So this would be the whole state I, and this is the whole state J. So this is the way we would write this diagrammatically. We can do the same thing with the one-body operator, but we did this earlier. So we can represent this diagrammatically. So this would just be a one particle, one hole type of excitation. That's the way we would interpret that one. Now, we have this factor of 1 divided by 4. There are 3 more possible contractions, so that all these contractions give us at the end the same matrix element. So plus 3 more similar contractions. So let's look at one of them. So let's bring it up again. So what we had now is a contraction here. Let me just set up my notes for it. So we had C of AI of AA, an AP dagger, an AQ dagger, and then we have AS, AR of AB of AJ acting on C. So in the previous case, we linked AA with AP, but now we could simply change AA with AQ, just to give you an example. So let's do that. So the thing we do now, instead of letting A go to P, we let it go to Q. We have then another contraction, which we keep as before. So we just take that one. Now what we can do next now, so this is an AI here. What we could do now is to let this one go to that. And we can let P go to J here. So again, there's going to be a minus sign. So when we write out the matrix elements, we will have -1 divided by 4. There's going to be a matrix element which now contains P, which now is equal to J. So that will be JA here. And it's going to be a V here. And then I have the last one where I'm going to have B. And then I'm having a matrix element here, which is given by I, anti-symmetrized. So if I look back at the way I organized the matrix elements, I had an AB and an AJ here. So I can always rewrite this one. This is actually going to have a plus sign. So I can rewrite this one in terms of 1 divided by 4 of AJ, of V, and IB, as we had before. And then we have 2 more types of contractions, which are pretty easy to see because now we interchange the 2 particle states, and then we can do the same thing with the whole states. And at the end, when we sum up all these terms, we get rid of the factor 1 divided by 4. So that means that when we look at this specific contribution here, where I had a delta C of H with delta C, when I'm now setting up everything, this is going to be rewritten in terms of a single sum of A and I. And we are going to get, we can write this in a way like this. I'm going to have a delta CIA, a delta CJB, and then I have an epsilon A, Hartree-Fock, with delta AB, delta JI, minus, and I have an epsilon I, Hartree-Fock, of delta AB, delta IJ. That's the first term. And then the next term here, so let's just multiply that one like this. We have plus, and then we have the final term, which I need to change page with. So if you've written it down, I'm just going to put it up. So there's going to be a term which goes like A, J, V, and then I have my term here with BI, anti-symmetrized. Now let me check. No, I didn't write it like that. I wrote it like this. Yeah, that's the way I wrote it. Now, one thing we can do now, and we are going to prepare the ground for the way we will rewrite everything. So I'm going to now introduce a new label where I define I as a particle hole configuration. And I is now going to be equal to the states A and I. And then I have my next one, which is J, which is going to be a new particle hole configuration, which simply contains B and J here. And then I'm going to define a quantity, which is delta epsilon I, J. which will now be given by epsilon A Hartree-Fock minus epsilon I Hartree-Fock and multiply with delta AB, delta IJ. I'm going to define yet another quantity. So I will define a vector, which is called delta C. So delta C now is a vector, and that contains all delta CIA. Then I'm going to define yet another quantity, so which I'm going to call A of AI and BJ. So that means I can rewrite this one as A of I, J. So these are just indices. So where the indices now refer to particle hole configuration. And that is going to be given by this specific matrix element, which I have, this A of J or AI. Let me just rewrite it here. So that will be, I'm going to rewrite it like, what did I do now? Let me just check one thing here. Yeah, I'm going to couple that one with the matrix element which we had. So we have a B J. No, wait now. I think I messed up things here. Yeah, okay, so let me just write this correctly here. So this is the matrix element of AJ, which we put up, of VIB. And if you look at the diagram, what we have is a particle hole configuration, where we have AI here, and then we have JB. So this will be the, refer to the label I, and this will refer to the label J. And it's common to actually rewrite this matrix element in a kind of strange notation. So you will see something like an A of I minus, of V, and then you have a J minus with B here, or BJ minus. And this J minus here, or I minus, is actually meant to indicate that these corresponds to the incoming state. So you can now think of an incoming one particle, one hole state like this, and an outgoing one particle, one hole state. So when you write this matrix element in this strange way, what we are thinking of, if you look at the process here, you have a one particle, one hole state and a one particle, one hole state, but the explicit matrix element is not written like a one particle, one hole state here and a one particle, one hole state here, which refer to the same vertex here. So it's a kind of strange notation, but I'm going to rewrite everything in terms of these indices I and J. And that's also because if you look at the terms here, these terms refer to a specific particle hole configuration. So if you then look at what we did here, this specific sum which we have is something which we now can rewrite in a more compact way. And you see immediately that this is something which we can write out in a matrix vector notation later. Because if you rewrite it in terms of these indices, which we introduced, this one and that one, then we can rewrite that last term which we had. So we can rewrite that specific sum for delta C of H of delta C here. We can rewrite that as a sum over I and J. And then we're going to have a coefficient Ci, which is actually this AI states, this one particle, one hole state. And then I have a delta Cj. And then I'm going to have a matrix element. Actually, I'm going to have this delta epsilon ij multiplied with delta ij, because this is diagonal, plus this matrix Aij. So this is the compact way of rewriting this specific contribution. So the way this matrix, this is going to look like, if we now think of this, because what we have is a vector C multiplied with a matrix and multiplied with a new vector. So what you have here, if you just think back to a vector times a matrix multiplication, if I have a vector X multiplied with a matrix X, this is nothing but a sum of ij, and then I have my xi, the matrix elements aij, and multiplied with xj. So the way I now rewrote this in terms of particle hole excitations is something which I can actually now rewrite in terms of a vector delta C, and this is this vector here, multiplied with a matrix, and this matrix is now a matrix which is going to contain, so we have a vector delta C, so this is now a vector, and the matrix is now going to contain elements. Let me just find my notes here, where we have a delta epsilon II, 1, 1, or we can actually rewrite it. So let me just rewrite this one, sorry for the mess here. So if I look at the first term, this term which we have here, this one multiplied with that one, this is simply going to be a delta C multiplied with a matrix where I have a delta epsilon 1, 1, there's a delta epsilon 2, 2, so this has only diagonal elements, and then I have the final one epsilon p, the final particle hole pair which I have, multiplied with delta C, another vector. So what you have here is nothing but something you can rewrite in terms of a vector. We have the specific component multiplied with a matrix, which the first term is diagonal. And then the next term is going to have non-diagonal elements, because what I would get then is a plus an A11, and then I would have an A12, and then an A1 up to the last particle hole configuration. This would go down to the A particle hole 1. Here I would have plus an A22. Here I would have a plus an A particle hole here. That would be the final one. So this is the rough structure of that specific contribution. Now, the final matrix we are going to look at will have these terms here along the diagonal. And for that matrix plus something more, which we have to calculate now, it would be sufficient for the Hartree-Fock stability that the diagonal elements are actually larger or equal than 0. That's a necessary condition, but it's not sufficient. So let's calculate the two other terms, because we have a new term, which is given by C of H, and then I have my delta C squared. So if we look at that term, so let's do the algebra here. So this is going to be equal to a C of H, and then I have my AI, and then I have my AB of AG acting on C here. So with this one, I can now set in the one-body operator. And when I set in the one-body operator, I'm going to get a contribution which looks like this, AP, AQ of AA. So if you look at the one-body operator, can you, just by looking at the contractions we have to do and using Wick's generalized theorem, because you have chains of operators where you cannot perform contractions between them. If you look at this one, what would you expect as an answer here? 0. And you could actually have guessed that without doing any calculations, because you have a 2-particle 2-hole state, which is created by this one. So this is actually a 2-particle 2-hole state. And you have a 1-body operator, and that can at most bring you back to a 1-particle 1-hole state. So you would then be calculating the overlap. In principle, what this leads to is you having to calculate the overlap with a 1-particle 2-hole state and a 2-particle 2-hole state, which you created, which is 0. So this term is 0 automatically. So this is one of the nice things with Wick's generalized theorem and normal ordered operators with respect to new vacuum, is you can just look at it in terms of excitations. And then you can say this has to be 0 without running any calculations. That means that the only term which survives is the one which comes from the 2-body operator, because that's the only one which can bring us back to a 2-particle 2-hole excitations. So we would have an AI of AA, AB of AJ with C here. So what we can do now is simply just to repeat this kind of exercises which we've been doing. So we would have this one which contracts with that one. And then we can contract AS with A. Sometimes this doesn't go too well. Let me just take that one away. So I contract this one, and then I contract this with B. But then you see that when I'm now performing the contractions, let's say with the I state here, then I'm going to have an interchange of fermion operators, so that gives rise to a minus sign. And then I have the final one here. So that's going to give me a matrix element, which looks like minus. So P is equal to J, and Q is equal to I. And then I have S is equal to B, and R is equal to A. So this is AB. There is a factor 1 divided by 4, anti-symmetrized. And then I can rewrite this one by interchanging I and J. So this is the same as IJ of V of AB. Now I can now perform 3 more contractions. So they're 3 pretty similar ones, and it's easy to see that. So we will have plus 3 more. And these 3 more, that give us at the end just one matrix element, which looks like this, AB, anti-symmetrized. And if I want to draw a diagram for that, what I would have is the interaction line here. And then I have an incoming particle state, A, whole state I. So this is A and B. And this is again state B and J. So this is a particle whole state. And this is also particle whole state. But this diagram is something which I would read as a 2-particle 2-hole excitation. So I create actually a 2-particle 2-hole excitation. And we see that when we look at this specific matrix element here, we have a 2-particle 2-hole state. And then in order for us to get back to something which is non-zero when we take the overlap, then the Hamiltonian here has to create also a 2-particle 2-hole state. And that is reflected in the final matrix element here, that we end up with a 2-particle 2-hole state. Reflected, so we would typically call this for 2-particle 2-hole excitation. And then there is also an exchange term here. And the exchange term is something which we can simply rewrite like this. So we can keep A and B fixed. So we have A and B. And then we would simply interchange the 2 whole states. So this will be an I, which we had here, and a J here. And that's the exchange term. So that's the way we would write a diagram. And just also keep in mind that many people, just for compactness, you just list this term here, and you still interpret that as a diagram which is anti-symmetrized, corresponds to anti-symmetrized matrix elements. So this is the way you would do that. Then it shouldn't come as a surprise. So I'm going to set up the final one. this delta C squared of H of C. So that has to be the Hermitian conjugate or the other one. And what you will see then is that this is going to give us A, B, V, and IJ when you run through the algebra here. So we have a particle Hall states, and we can now rewrite this in terms of a new matrix element. So I'm going to define an object B of AI and BJ, which is again given by this B, IJ. And this is something which will now be given by these matrix elements IJ, V, and AB. So when you look at the diagrams, it's easier to see it from the diagrams that we have a particle Hall state here, which now corresponds to A and I. And we have a particle Hall state on the right vertex, which now corresponds to this subscript J. But when you read it in terms of a matrix element or an integral, you actually have these specific order of the indices. So sometimes it's easier to see things diagrammatically, because diagrammatically then you have a vertex here where you have a particle Hall pair, and then another particle Hall pair here. And this is the same as saying that you have an incoming particle, which then gets destroyed, and you have a Hall state coming out here. So that means that this particle here gets destroyed, and then you fill this Hall state, I. Now we can rewrite everything in with these matrices B, which we have here, and this matrix A, which we defined here, and this other matrix delta IJ, which is just a diagonal matrix, where we have the single particle energies along the diagonal. We can actually rewrite the problem, and it's not so difficult to see that the problem is something we can rewrite in terms of a contribution. So we have this delta E here. If we now look at so we have delta E, which is going to be given by these different terms. Let me just wipe this out here. So when I look at my contribution of C prime of H of C prime divided by this term here, so I'm going to rewrite this in terms of E Hartree-Fock. And then you can actually show that we then get these contributions which we've been looking at. And I'm going to call these terms which we have collected as a delta E. And there's going to be a term here which runs over the normalization factor. And this is AI. And this contains delta CIA. So the denominator is not that interesting, but the delta E is the one which is interesting for us. And I can rewrite this in terms of a matrix where I have a factor over half. And you will see quickly why we have this factor over half. So this vector X contains now a delta C and a delta C conjugate, complex conjugate. And the matrix M, so the factor over half, follows from the fact that the matrix is here. So we have this delta epsilon plus this matrix A. And then I define a matrix with the B's. And I have a matrix B here, which is the complex conjugate of B. And then I have a delta E, delta epsilon plus A, complex conjugate. So if I set this up, what I will have then is the following. So I'm going to get a delta C. This is transposed, delta C transposed, and Hermitian conjugate. And I have the matrix delta epsilon plus the matrix A. And then I have B as a matrix because I have a set of particle Hall configurations. And delta epsilon plus A. And this is multiplied with this delta C and delta C complex conjugate. If I write this out, you will see now that this simply corresponds to the type of matrix elements which we put up. So if you look at the write out of this one, I will have a C plus, a delta epsilon plus A, times delta C plus, and this is C, and this contains B of delta C, and then I have plus of delta C of B, and then plus the final one of delta complex conjugate transpose of delta epsilon plus A of delta C. Now, if you look back at what we had earlier, if you look back at the terms like this one, just to convince yourself of what is happening here, and this contains a factor of a half in front of it. If you look at these two terms, what these two terms are actually going to give us is a sum over I and J, and then I have a delta C of I, and then I have this delta epsilon ij of delta Cj plus a sum over I and J, and then I have my delta Ci, and then I have the matrix element Aij, and then I have my delta C of J. So this has a factor of a half, and then I have a similar factor plus 1/2, and which then contains the same term here, but then it has the complex conjugate one, and that is, when I have that one of Ij, this is the same as Aj. So this factor of a half here comes because I've written the matrix in this specific form. So I have delta E plus A here, and then I have a delta E plus this A complex conjugate, and using the hermeticity of the operators here and the integrals which we have, we see then that the two factors of a half, they give us back the original expression. Now, the thing which is interesting for us then, and this is where we're going to stop today, is that what we want now, so let me just bring this up. If we are looking at this problem here in terms of this specific matrix, what we want is that this delta E should be larger or equal than 0 in order for this state here to be a minimum. So coming back to the requirement that this Hartree-Fock state is a minimum, what we need now is that this delta E should be larger than equal than 0. And that means that the matrix M has to be positive definite or semi-positive definite. To be semi-positive definite. Which means that the eigenvalues of M are larger or equal than 0. Now, a necessary but not sufficient condition, necessary condition is that the diagonal matrix elements are larger than 0. So if you look at this matrix here, this specific matrix which we have here, if you now have 0 contributions from the non-diagonal ones, then the eigenvalues are just given by the diagonal matrix elements. So a necessary condition when you don't want to diagonalize the matrix is actually that these diagonal elements, the necessary condition, the diagonal elements should be larger or equal than 0. So what we have then is an epsilon A Hartree-Fock minus epsilon I Hartree-Fock plus this specific matrix elements, which is given by Aj of V IB Hartree-Fock, anti-symmetrized, are larger or equal than 0. So that means that you can actually look at specific matrix elements, and then from these matrix elements, say something about whether Hartree-Fock theory is going to be stable or not. So that is a condition which you can look up immediately, and that will tell you whether that state you have found is the minimum from the Hartree-Fock calculation. So this is a kind of way to actually establish a kind of minimal way of finding the stability condition on the Hartree-Fock equations. So tomorrow, we are going to conclude this part on the formal Hartree-Fock piece by looking at Fowler's theorem. The relation which you see here is something you can use in connection with the midterm, because at the end of the midterm exercises which you have, there is actually the possibility to derive the condition on the Hartree-Fock equations in terms of the matrix elements. So you will find out whether the matrix, the Hartree-Fock solution is stable or not in terms of the value of the interaction matrix elements. Okay, I'm gonna stop the recording here now.